In this video, I will go over the homework that follows the lecture on the first of the two absolute convergence tests called the ratio test. And as always, I hope that you watched the lecture before attempting the homework. And now let's go ahead and take a look at the homework. So the first question is to analyze the convergence of this series. And normally we would do the divergence test first, or normally I guess we would try to identify whether it's geometric or p-series, which it isn't. Then we will try to set up the divergence test by finding this limit, but when this limit is a bit too hard to find, then we can totally skip this step. But anyway, and only then we will start thinking about applying any of the convergence tests. Now, here we are asked to apply the ratio test, so let's make a habit of declaring our test. And in ratio test, we're going to find the limit of the ratio of the nth term, or rather n plus 1th term, over the nth term. And the absolute value in case if there's a negative sign somewhere there. And now this becomes, after you simplify everything, it just becomes 3, so this is reduced with that, so we just have 3/5 of n plus 1, which is same as 3n plus 3 over 5n. And here we see that we don't need absolute value because everything is positive, and this limit is equal to 3/5, which is less than 1, and therefore this series converges absolutely. This is an absolute convergence test, but for positive series, absolute convergence is the same as regular convergence, so this series converges. The term absolutely or conditionally makes sense when you have an alternating series. Since we don't have to write that. All right, another convergence question. We have n factorial over 9 to the power n times n. As always, we try to recognize this as a geometric or p-series. No, we try to run the divergence test. Here it's going to be problematic because finding the limits of factorials is not so easy, so we're going to bypass this one, and we're going to start with the ratio test. So to set up the ratio test, we're going to find the limit of the ratio of the n plus 1th term over the nth term. And let's simplify this. Sometimes we get some limits that are not trivial, so some limits may take longer than others. So here I'm just handling the expression first, rewriting it, and now we're going to start simplifying. N factorial and n plus 1 factorial have a lot in common, and as a matter of fact we can rewrite n plus 1 factorial as n plus 1 times n factorial, so n factorial is gone. Now 9 to the power n plus 1 can also be written as 9 to the power n times 9, and then 9 to the power n is gone. So then also interestingly enough, we can reduce this n plus 1 with this n plus 1. So the only thing we have left after simplifying everything is n over 9, and this is equal to infinity. So since this ratio is greater than 1, we conclude that this series diverges. But we would probably also conclude the same using the divergence test. It's just that limit is less trivial than the one that we found. So that's the advantage of the ratio test. Alright, so the series diverges. And just a quick remark, I did mean to put absolute value there, but then since everything is positive, we would just stop writing it anyway. Next question. Having factorials is pretty much the hint for using the ratio test, but in this case we would always try to recognize in general, like whether it's a geometric or p-series. The answer is no. We would try to set up the divergence test by trying to find this limit. Finding limits of expressions with factorials is not trivial, so we're going to bypass this one and we're going to jump into setting up the ratio test. So we set up the ratio test by finding this limit of the ratio of the n plus 1th term over the nth term. Rewriting it, what do we have? We have n plus 1 factorial over 5 times n plus 2 factorial times 5 times n plus 1 factorial divided by n factorial. And this is actually interesting. Now I'm noticing how a lot gets simplified here, so there's actually a nice shortcut there. But let's see. We have, so n factorial and n plus 1 factorial can be simplified like this. We have n plus 1 left. N plus 1 factorial and n plus 2 factorial can be simplified like this, so we have n plus 2 left. 5 and 5 are gone, so we have the limit of n plus 1 over n plus 2, which is just 1, which is less than, well, actually, hold on. If it's 1, that means the test is inconclusive. So what do we do when the test is inconclusive? So technically we are stuck. However, if you pay attention to all these factorials, you can also notice that this can be simplified to 1 over 5 times n plus 1, which diverges. So we know that this series diverges by the limit comparison test, for example. But the question wasn't about whether the series diverges or converges. The question was to use the ratio test. So even though we do know that this series diverges, we're going to answer the ratio test as inconclusive. All right, let's move on. We have another series. This is just a p-series, so we know the answer But the problem is asking us to use the ratio test. And for p-series, ratio test should be the same. It should be conclusive. Let's see. So in the ratio test, we're going to set up the limit as n goes to infinity of n plus 1th term, or let me see, over the nth term. So what we see here is n goes to infinity, 7n to the power 9 fives divided by 7n plus 1 to the power 9 fives. 7s are cancelled. We have limit of n over n plus 1 to the power 9 fives. I see. So the test is actually inconclusive here. That's weird. Right, I guess we did see that example in the previous exercise. Like, it was just a harmonic series, but the test was inconclusive. So there is value in doing what I suggested earlier and actually checking and recognizing the most common series, such as geometric and p-series. So this is a p-series with p equals 9 fifths, which is greater than 1, therefore it converges. But the ratio test is inconclusive. So the series converges, but the test is inconclusive. And this was it. If you have any questions, please let me know.